All right, we're going to dive right in. Section 3.1, we're going to talk about complex numbers. Chapter 3 digs down a little deeper into the quadratic function, the parabola of our basic functions, the x squared function. So that's the one for these next 4 sections we're going to deal with the most. In fact, we'll probably start section 3.2 today, and we will get started, or we'll remind ourselves about the graph of that and another way that we can look at it. So before we do that, this first section, I'm guessing for most of you, if you took intermediate algebra here at Polk State, this first section, most of it, probably 75, 80% of it is going to be nice in review, which is a good place to be. That helps us. So what we're going to talk about is complex numbers. They pop up a lot, especially as you get higher up in math. If any of you have desires to go into any sort of engineering field, you're going to encounter complex numbers all the time. And if you're math terminal, if this is your last math class, well, you're going to encounter complex numbers on the next test. So at some place in your future, you're going to find them. So what I included on the sheet that I gave you was just a little graph to kind of explain where the idea for complex numbers germinated. So we will talk later in this chapter about solving quadratic equations. But again, probably something, even if you didn't have intermediate algebra, you tested in this class. So you had a high school class and you solved something like this. X squared minus 1 equals 0. Okay, whether you did it by factoring or whether you did it by adding the 1 over and taking the square root, that probably looks sort of familiar, and we'll come back to that when we get to the third section of this unit. But so if you remember, x squared minus 1, this is my basic x squared function, and it's been dropped down 1. So just real quick, this is not perfect, but it's going to get the job done. This is the x squared minus 1. So when you solve this equation, you're finding what's called the roots of the function, or the zeros of the function, or the x-intercepts. All of those 3 things are equivalent terminology in math. Roots, zeros, x-intercepts. And so you can see, since I moved the parabola down 1, I have 2 x-intercepts. I have one right here, and I have one right here. So when you solve a quadratic equation, that is what you're doing. You're finding those x-intercepts. So the question, at some point in the math past, some crazy mathematician had this idea. What happens instead of moving the parabola down 1? What if I move the parabola up 1 unit? And that's the graph that you see on your sheet. So we've moved the graph up 1. And so here's my parabola. Again, not perfect, but it's just a sketch. And we see, where does that graph go through the x-axis? Not a trick question. It doesn't. Okay, so there are no real numbered roots or no zeros, and it definitely doesn't go through the x-axis. But not to be deterred, what happened was, I don't know the history of it. It would be an interesting project, but whoever determined this decided, here's what we're going to do. We're going to subtract 1 from both sides, and we're going to say that x squared, the solution to this, okay, the solution to this, if it exists, would be the number that when I square it, I get -1. And probably for your whole math lives, up until the first time you heard about complex numbers, you were told, well, that never happens. Anytime I square something, I get a positive value. Well, this is now the definition that we come to. And this is the key bit of information that we are going to go over a whole bunch of times in this class. We are going to define the solution to this. Okay, we are going to define, where is this equal to 0? And so here's the definition. Okay, this is the key bit of information that you need to know that we're going to use a whole bunch. So if you've not seen this, you're not behind the curve at all. Little math humor there, behind the curve. Anyway, you're not behind the curve at all. You didn't get it. It's not that funny. It's real cold in here. I totally understand, but I'm entertaining myself. The definition is this. I'm going to define a number that solves this equation, and I'm going to call it I. And I is equal to the square root of -1. And this is the definition of what's called, I is called the imaginary unit. corollary, meaning the equivalent to this definition, okay, this is going to be saying the same thing, is that the corollary is that I squared, okay, so I, the imaginary unit, is the number that when I square it, I get -1. Okay, so this is the core concept to this section. Okay, this definition that we have just invented, and we didn't do it, somebody did it, but a new number was invented called the imaginary unit, and the principle behind it is that it's the number that when I square it, I get -1, meaning it is the number that when I plug it into this equation, it solves this equation right here. Okay, so where we go with that from the imaginary unit is we develop this idea of what's called, I just erased the word, but I guess I get to rewrite it now. Let's use a different color just for fun. So with the imaginary unit, we create this whole new set of numbers, bigger than the set of real numbers, which is what you do most of your algebra on. And the complex numbers are this. And I started the definition on the sheet. If A and B are any real number, so it doesn't matter if they're decimals or fractions or square roots or what, any number at all, then we define a complex number to be A plus BI. Any number that I can write in that format is called a complex number. So again, I'm assuming if this is review for you, that's great. If it's not, that's okay. I'm assuming that we're all on the ground floor together, and we're going to all rise together. So here's just some examples of complex numbers. So for instance, like 5 plus 2i, that is a complex number. The real part is 5. The imaginary part is 2i. And I can do that. You can write down a complex number with any values. I can have pi minus 1/2 i. The real part is the number pi. The imaginary part is -1/2 i. Now, I forget, our book calls these, okay, when there is both a real part and an imaginary part, I just call it a complex number, okay, because I'm kind of laid back in this, but our book, and I don't want you to get hung up here, our book's going to call this a non-real complex number. The reason they're being extra specific about that is technically real numbers are complex numbers. So for instance, if I just give you the real number 3.7, well, yes, that's a real number. It's a number we've always used, but it's now also a complex number with no imaginary part. Okay, so I can still write it. So it would be 3.7 plus 0i would be another way to write it. But 0 times anything is 0, so I just leave it off. So real numbers are technically complex numbers as well. So 3.7, this is a real number, but it's also in the set of complex numbers. If I leave, so that's what happens if you leave the imaginary part off. We get the set of real numbers, which we're already used to. What happens if I have no real parts? So what happens if I have like -7i? Well, I will just call this an imaginary number. It's also a real number, okay? Just a real number with no, I'm sorry, it's also a complex number. It's a complex number with no real part. But our book, again, they get a little more specific, and they call this a pure imaginary number. When you do your homework, I just don't want you to get to stumble because you don't use the exact right terminology that our book uses. I am fine with when you are conversing about it with the shorthand and just saying that this is a complex. I mean, all of these are complex numbers. Okay, so I'm just going to call this a complex number. You can call that a complex number, but it's an imaginary number. That's a real number. You can call it a complex number because that's what they all are. We have just now made our world of numbers bigger with the imaginary unit. So we're going to go through, we're going to do a few things based on the imaginary unit. First thing we're going to do is we're going to talk about how to simplify numbers and make them into imaginary numbers. Then we're going to go through the operations that you have known and loved since elementary school. And we're going to go through them with complex numbers. So first thing, this is example 1 on the sheet. It says, let's simplify the square root of negative 16. Now, I'm going to do this in 2 steps, okay? I want to show you exactly why this is true, but you don't have to do both these steps. Once you've done 1 or 2 and it clicks and you see what's going on, that is totally fine. But I just want to remind you of our good friend, the product rule of radicals from our intermediate algebra days. And so what I'm going to do is I'm going to take the square root of negative 16 and I'm going to break it up into things I can take the square root of. So negative 16 is negative 1 times 16. And then what the product rule of radicals says is when you have a product under your radical, you can think about those things individually. So again, this is the stuff after you've done 1 or 2. If you don't need to write all this down, don't write it all down, okay? That's fine. I'm just showing you what's going on. So I can break this up into the square root of negative 1 times the square root of 16. By the way, this is a cardinal sin of math. If this is a plus sign, you cannot just take the square root of sums and differences. Okay, I don't think it's going to occur here, but I just don't want you to break up numbers into sums of things and then take the square roots of the parts. This does not work. Okay, you'll get the wrong answer every time, only when it's a product. And so now, here we go. What's the square root of 16? Yeah, we all know that. What's the square root of negative 1? That's the definition. Okay, that was the thing that was right here that I just erased. The square root of negative 1 is I, so we get the number 4i. So the square root of negative 16 is the imaginary number 4i. I squared is equal to negative 1 without the radical. Okay, so here's the definition. The definition is these 2 things. I is the square root of negative 1, and I squared is negative 1. Okay, so that's the 2 things. So this is the square root of negative 1. So it's I. All right, if you would, I'm going to give you 20, 25 seconds. Exercise 1 says do the same thing with the square root of negative 81. Yes, ma'am?
So when it says definition of complex numbers, if A and B are real numbers, then
A plus BI is a complex number. I didn't write B as a complex number, sorry. All right, square root of negative 81. I'm going to break this up into negative 1 times 81, and now you help me. What's the square root of 81? 9. What's the square root of negative 1? That is the definition. That is I. Fantastic. You're doing great. All right, we're going to keep on doing this. Different number. I'm going to help you with this one. We're going to simplify the square root of negative 75. So this is incorporating, again, a skill that at some point you've been exposed to, whether or not you remember it at this point. Well, hopefully this will jog your memory. We're going to use the product rule of radicals on this. And so negative 75, I'm going to start with the negative 1. Then here's the question when I have my number. What is a factor of 75 that is a perfect square, meaning I can take the square root of it? 25. 75 is 25 times 3. So it just becomes a calculator problem. If you get a number that maybe isn't super familiar, you just take your calculator and divide into the perfect squares. Perfect squares, 2 squared is 4, 3 squared is 9. So these are the perfect squares. And then 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 is 81, 10 is 100, and it's very relaxing. You can keep doing that all day. So as you are asked to simplify radicals, you're looking for a number on this list that divides into this number right here. And you all correctly told me, it was a great job, 25. So now I'm going to use the product rule of radicals. Because the product rule of radicals says, okay, I've got a product here. I've got 3 things multiplied together. So what that means is I can take the square root of each one individually. So square root of negative 1, that is I, yes. Square root of 25, 5. Square root of 3? It's just going to stay the square root of 3. It's an irrational number. We're not going to write it down because it would take you forever to write it down. Now, a notational thing. I'm going to put the square root of 3 just because I'm a messy writer, and also this is what most textbooks do. I'm going to put the square root of 3 over here after the I. If you write 5 square root of 3i, that's fine. It's not wrong, but just be careful with your radical. The reason it's written like this instead is if you get real excited, because math is super exciting, and you kind of draw your radical like that and accidentally put the I under, now you're communicating something different, okay? And that's not something we're going to get into in this class, but if you go up in math, okay, then you're communicating something unintentional, okay? So that's why it's just safe when you have some radicals to put the I in front of it, okay? Does everyone understand why I'm doing this for my notation? Okay, I'm not trying to confuse you. Actually, I'm trying to not confuse you in the long run. All right, here's another one for you. Simplify the square root of negative 24. All right, negative 24. I'm going to give you the negative 1. I think we all see the negative is there. Now, what perfect square factor is there of 24? 4. Yeah, it's 4 times 6. Fantastic. If you used 8 times 3, 8 times 3 does give you 24, but that doesn't help you simplify because you can't take the square root. Well, 8 doesn't have a nice perfect square root, and 3 doesn't have a perfect square root. You can't use 12 or 2 for the same reason. So that's why 4 is the one for us. So here we go. The square root of negative 1 is I. The square root of 4 is 2. The square root of 6 is square root of 6. And there's my imaginary answer. Okay, so that's simplifying square roots that have a negative under them. So we're now going to take that skill. We're going to build on it. But before I do, is there a question, comment, or concern? Okay, so the next thing that we're going to level up and do is I want to multiply these two numbers. Now, this same thing, there'll be some examples in your homework of dividing. You do this same process. I just picked a couple multiplication examples just for kicks. So let's say I have the square root of negative 5 times the square root of negative 10. Now, I understand you've come here and you're used to working with real numbers. So right away you say, oh, hey, I'm multiplying two radicals, so I can multiply the stuff under the radical. And so I'm going to have the square root of negative 5 times negative 10 is positive 50. Unfortunately now, we have to make sure we're following good procedures because now I have a negative under here. And so some of the old ways don't translate over directly. So what you have to do first, when you're multiplying radicals with a negative under it, or when you're dividing radicals with a negative under it, first thing is you have to write them as imaginary numbers. Okay, that's step one. It's required. There's no way around it. So we are going to do what we just did here for both of these. Now, neither 5 nor 10 has a perfect square factor. Okay, so here's what I've got then. The square root of negative 5 is going to be I squared of 5. All I did was simplify that square root of the negative 1 under there and made it I. Just didn't write it out. Is everyone comfortable? Anyone uncomfortable with what I just did? Yes, ma'am. Yes, I just skipped this step right here and cut right to the negative, gives me I. How about the square root of negative 10? What is that as an imaginary number? Okay. It's I square root of 10. Again, same thing. If you need to, if you're not there yet, then don't let me do that step. That's fine. Nothing wrong with that. So we got pencils. All right, now here is where the other part of the definition is going to kick in. We just used the square root of -1 is I, that first part of the definition. Now, here we go. I'm going to multiply these two things together. What's I times I? Yeah, just treat it like any other variable, like if it was a variable. So we got I squared, great. Now that both things under the radical are positive, I can apply my product rule of radicals. And so 5 times 10 is square root of 50. And maybe you saw this ahead of time. The more you work with these things, the better you get, the more shortcuts you can take. I totally get it. What is I squared defined to be? That makes this negative, so we've pulled the negative outside the radical. 50 is 25 times 2. And so by the product rule of radicals, the square root of 25 is 5. I've got that negative in front of it, and then the square root of 2 stays under the radical. I am guessing with a touch of review, if there were no negatives under here, I could have given this problem and you all would have gotten it. Okay, the only difference here is before you can do the multiplication, you've got to simplify the negatives that are under the radical. Okay, that is the first step. So you'll see right to the right of that, there's a first problem. It says multiply the square root of -9 times the square root of -25. Do that one first, please. All right, so if you don't need to write this step, that's totally fine, but I'm putting this up here just in case anyone needs the visual. So the square root of -9 is square root of -1 times 9. The square root of -25 is square root of -1 times 25. So when I simplify, what does the square root of -9 become? 3i. What's the square root of -25 become? Fantastic. Now let's multiply. 3 times 5 is 15. I times I is I squared. And then the last step is to apply the definition. It now kicks in. What is I squared equal to? Yeah, so this is 15 times -1 or -15. Fantastic. Do the one that's right below it. Square root of -6 times the square root of -15. Square root of -6. How does that simplify? I square root of 6. Perfect. Square root of -15. I square root of 15. First step is to resolve that negative that's under the radical. Okay, put it in our new notation. That's applying the definition that is the whole substance of this section that we're talking about. Now I will do the multiplication like I was tempted to do to begin with. I times I is I squared. 6 times 15, that's 90 underneath the radical. So I have two things I've got to simplify. The I squared doesn't stay that way. And then 90 has a perfect square factor. So I squared is -1, so that makes my answer negative. Perfect square factor of 90 is 9. It's 9 times 10. Again, if you have a calculator, it's just a matter of going down the perfect square list until you find the perfect square that goes in, as long as there is one. And so now I have the square root of 9, that's 3. The negative is out in front, and then square root of 10. And there's my simplified answer. So we started off with our definition. I is the square root of -1, and its corollary, I squared equals -1. And then we talked about simplifying radicals that have a negative under them. And then we applied that to this instance of multiplying radicals that have negatives under them. And now we're going to go through and we're going to look at the 4 basic operations that we know how to do with real numbers. How do we do them with complex numbers? Before we turn, I know you turned the page. Questions, comments, concerns? All right, I'm trusting you. No need to be shy. First thing we're going to do is we're going to add complex numbers. So you see that first example on the sheet is 4 plus 3i, and we're going to add to that -6 plus 8i. So I just want to link this to something that I am certain you already know how to do. If instead of i's, if these were x's, okay, if these were binomials, and I asked you to add these two binomials, what would you tell me we need to add? The like terms, exactly. Same thing. We're just going to add the like terms. We're going to add the real parts, we're going to add the imaginary parts, and then we're going to be done. So when I add these two things, what do I get when I add the real parts of these numbers? 4 plus -6 is indeed -2. Great job. And what do I get when I add the imaginary parts of these two numbers? 3i plus 8i is 11i, and we're done. There you go. Added the real parts, added the imaginary parts. If there was a third complex number, you would just add all the real parts, all the imaginary parts. That's it for adding. Do exercise 5 on your sheet, please. What's my real part to the answer? 9 and 8 is 17. Fantastic. And then what's the imaginary part to the answer? Okay, -4 plus 7 is plus 3i. Boom, done. Before we go on to subtraction, is there a question? Okay, I'm hoping that you would stop me. I'm trying to balance the line between boring you to death and going too fast, so just let me know how I can do better. Here's the next one, -2 minus 11i, minus, this time we're subtracting, 13 minus 5i. Now, if you had had me way back in introductory algebra, or even in intermediate, I would have proposed this to you when we're subtracting polynomials, because we messed this up a lot. Okay, and I want you to avoid any simple mistakes that can be easily avoided. This minus sign, what I'm going to do so that I do not mess up any signs of any numbers is I'm going to distribute that minus sign. So the first thing I'm going to do when I subtract is I'm going to take the -2 minus 11i, and then a negative times the 13i is, negative times 13, it's not 13i, pardon me. That is -13, and then a negative times a negative is plus 5i. Now, I know some of you can do it without distributing. I totally get that. But especially on tests when there's a little bit of pressure, you know, and you're maybe trying to hurry, I would recommend doing this because I see more simple arithmetic errors by just avoiding doing this one thing. Okay, so just make sure you distribute. Now I'm going to collect the like terms. The real parts, -2, -13 is -15, and then -11i plus 5i is -6i. And there's my subtraction when I subtract those two complex numbers. So do exercise 6, a subtraction problem for you. That is right to the right of the problem that I just did. First thing I'm going to do is distribute. A negative times a -5 is +5. A negative times a positive 13i is a -13i. Now I'll collect those like terms. 12 and 5 is 17. That is the real part. And then 6i minus 13i is -7i. There's my complex answer. I've got one more problem that combines both adding and subtracting. So if you do exercise 7. When I go to do this problem, what am I going to distribute this minus sign through? Just this one. Okay, don't take the minus sign all the way back here. What's the sign in front of this complex number? A positive. Okay, so that's the reason I gave this example, is just keep the signs with the individual parts. So again, the first thing I'm going to do is I'm going to resolve that minus sign, then I'm going to add my real parts, add my imaginary parts, and I'll be done. So this is going to be -4 plus 3i, then I have a -6, and then plus 7i, and then nothing changes here. Then I have plus -6 plus 8i, or -6 plus 8i. Here goes. Real parts. -4 and -6 is -10. And then -6 more is -16. And then 3i and 7i is 10i, plus 8i more is 18i. Yeah.
On the very end of that problem, with the plus -6 plus 8i, I thought that would be a negative.
Yeah, it is. You're totally right. Adding a negative is just the same thing as a minus. Yes. I just kept that notation because, for whatever reason, a positive times a negative is a negative. Positive times a positive is a positive. You can write it like that. Yeah, either way. All right, so good questions. That's adding, that's subtracting. Before we move on to multiplication, any questions, comments, concerns? All right, now I don't know. In my intermediate algebra class, again, if you're here, I go through multiplication, but not all of them do. Okay, so if there's anything that you're fuzzy on, let me know. Okay, so just make sure you're asking the questions that you need to ask. So multiplication. So my example of multiplication is 4 plus 3i times 6 plus 2i. Once again, I'm going to ask you this question. If this was introductory algebra, and these i's were x's, and I said, how are we going to multiply two binomials? What would you tell me in return? Yes, we have our acronym FOIL. First, outers, inners, last. It reminds us to multiply every pair of terms together. Now, just remember, okay, this isn't a variable. I means something, so we're going to have something to simplify at the end. That's the only thing you've got to remember that's any different than if this was multiplying two binomials that you've done before. So here we go. First, outers, inners, last. So my firsts, 4 times 6 is 24. My outers, 4 times 2i is positive 8i. My inners, 3i times 6 is 18i. And then my lasts, 3i times 2i. What's 3i times 2i going to give me? Okay, 6i squared. Don't forget that I squared. Is everyone tracking with me? Are we straight so far? Okay, before I collect my like terms, because that's, I'm sure, what you're going to tell me to do next, I want to take care of one thing before I collect the like terms. Right here, I have a positive 6i squared. What is I squared? Negative 1. So plus 6i squared, that term really is what? Negative 6. I'm just going to put a negative 6 right there above my box. Now I'm ready to add my like terms. So my real part, I've got the 24 up here. I've got the negative 6 right here. That is 18. And then my imaginary parts, 8i plus 18i is 26i. Does everyone see what I did there with that I squared? That's the key step. All right, do the problem that's to the right, exercise 8. 5 minus 4i times 7 plus 2i. I'm just going to get started. Check your work with my work. We'll meet up at the end here. So 5 times 7, those are my firsts. That's 35. 5 times 2i, that's plus 10i. Those are my inners. Negative 4i times 7 is negative 28i. And then last, negative 4i times positive 2i is negative 8i squared. Are we all looking at the same terms before we roll to the finish line? Okay, so again, before I collect the like terms, this is negative 8i squared. The I squared is negative 1, so that means negative 8i squared is equal to what? Positive 8. A negative 8 times a negative 1, because that's what I squared is. Negative 8 times negative 1 is positive 8. Now I'll collect these like terms. 35 plus 8, I believe that's 43. You should always check my arithmetic. 10i minus 28i is negative 18i, and there's my multiplication. One more multiplication example. So again, if you have a question, comment, or concern, get it in. Please do the next one, exercise 9. Here we go. My first 7 times 7 is 49. My outers, 7 times negative 5i is negative 35i. My inners, 5i times 7 is positive 35i. And then 5i times negative 5i is negative 25i squared. Are we looking at the same 4 terms? Any questions about any of those terms? All right, so one more time. I've got negative 25i squared. That term changes into what? Positive 25. This is negative 25. I squared is the same exact thing as negative 1, so negative times negative is positive. And now 49 plus 25, that is 74. And then negative 35i plus 35i, those cancel. I'm left with that. We good? All right, now I picked this example on purpose as a transition to the next thing. What's curious to you, or maybe nothing is, but I'm going to ask the question anyway. What's curious about the answer that I get when I multiply those two complex numbers? Yeah, the imaginary part's gone. It's just a real number. Okay, so I multiplied two complex numbers, two numbers that have an imaginary part, and I end up with something without. And so I picked this example because 7 plus 5i and 7 minus 5i, these are an example of what's called complex conjugates. What the conjugate is, what the complex conjugate is when you have the same two terms, but the sign of the imaginary part is opposite. So the sign of the imaginary part is opposite. That's what makes these conjugates. And this is going to be a useful tool. Being able to get rid of the imaginary part is going to help out for our last operation on complex numbers, which is division. And in fact, division doesn't even require any division when we go to do it. So for instance, if I want to divide these two complex numbers, 7 minus I and 3 plus 2i. Now, you may or may not remember from the rules of dealing with division that I can't just divide the real parts and divide the imaginary parts. If only it was that simple. You can't just divide parts of terms. So I need something else to do. So something we talk about way at the end of intermediate algebra is the idea of what's called rationalizing the denominator. And in case that doesn't sound familiar or you don't remember, the whole purpose of rationalizing the denominator is when I have a square root, which I do in the denominator, and I want to get rid of it. I want to have no more square root. And so the way we did that with square roots and the way we're going to do that with complex numbers is we are going to multiply the top and bottom by the conjugate of the bottom. We're going to multiply by the number that will get rid of the square root. Notice there's no more square root in this number. So tell me, please, what is the conjugate of the denominator? The conjugate is what you get when you change the sign on the imaginary part. Okay? So the conjugate is all of this, 3 minus 2i. Now, I'm not putting parentheses around this just because I don't want to gum this all up, but they're implied. Okay, so we're gonna FOIL here. Okay, it's this whole number times this whole number. Remember, with any fraction, if you multiply the bottom of the fraction by something, you have to multiply the top by that exact same thing. So I'm going to multiply by 3 minus 2i on the top. So just like any time in the past when maybe you've added fractions or you've reduced fractions, we have the same thing in the top and the bottom. This is just 1. 3 minus 2i divided by 3 minus 2i is just 1. They would cancel each other out. Okay, so we're not changing the fraction, but what we are going to do is we're going to create a new number that has no I in the denominator, and then I'll show you why that matters. So here goes. All I'm going to do, and I asked you if there was a problem with foiling a minute ago, is we're just going to FOIL twice, tops and bottoms. So in the top, 7 times 3 is 21, that's my first. 7 times negative 2i is negative 14i, that's my outers. Negative I times 3 is negative 3i, that's my inners. And then negative I times negative 2i is positive 2i squared, that's my lasts. All right, in the denominator, same thing. My first, 3 times 3 gives me 9. My outers, 3 times negative 2i is negative 6i. My inners, 2i times 3 is positive 6i. That's why the conjugate is important. These two terms should have opposite signs so that they'll cancel. And then 2i times negative 2i is negative 4i squared. You've done all the hard work. Okay, the rest of this is going to be downhill. We're going to combine our like terms, and then we're going to write our answer as a complex number. That's the key. Okay, that's the key step, the key bit of notation. So when I go to write this as a complex number, this last term right here, positive 2i squared, what is that really? This in the bottom, negative 4i squared, what is that really? All right, here we go. So 21 minus 2 is 19. Negative 14i minus 3i is negative 17i. Doesn't matter that there's still an I in the top. We want it there. In the bottom, 9 plus 4 is 13. Negative 6i plus 6i, those cancel. So we've accomplished our goal. There's no more I. There's no more imaginary part in the bottom. And that leaves me with one final thing to do. Don't leave your answer like this. This is still a ratio. It's a ratio of a complex number and a real number. We want our answer to be a complex number. It should have just a real part and an imaginary part. So what I'm going to do is I'm going to distribute. I'm going to take this 13 and distribute it. So my real part to this is going to be 19 over 13. That's my real part. And if it's if you can reduce it, reduce the fraction. This one can't. Minus. What do you think the imaginary part's going to be? 17 over 13, I. There you go. This is a complex number. There is a real part represented by this fraction. There is an imaginary part represented by this fraction. And now we're done. So I have an example for you. Do example 10. I'm going to give you 15 seconds to think about and write down what you think the conjugate is. And if you're confident, you can keep going. But if not, pause there, and I'll ask you what you think it is in a moment. What is the conjugate that I'm going to multiply both numerator and denominator by? Boom. All you do is you change the sign on the imaginary part, so it's 4 minus I. Great. Now do the busy work. All right, so I'm going to start my foiling. If you're still working, keep working. There's nothing wrong with that. Just a bunch of steps here. So here goes. My firsts, give me 20. My outers, negative 5i. My inners, negative 8i. My last, positive 2i squared. If you have a question, comment, or concern about any of my terms that are different than yours, let's talk about it. My firsts, 16. My outers, minus 4i. My inners, plus 4i. My lasts, negative I squared. As I've done on the last couple problems, positive 2i squared becomes negative 2. Negative I squared, that becomes plus 1. And now I'm ready to rumble. 20 minus 2 is 18. Negative 5, negative 8, that's negative 13i. 16 plus 1 is 17. The i's cancel. That's good. That's what I want. That should happen. That's why we multiply by the conjugate. And then to answer the question, at long last, I will write this as a complex number. So my real part is 18 over 17. And my imaginary part is 13 over 17. And we're done. Any issues with dividing? It takes a little time. I get it that you're multiplying two things, two pairs of binomials, but that's all you have to do there. All right, last thing then. So we've talked about all the operations that we would do with real numbers. The last thing is what happens if I have powers of I that are beyond 2? How do I simplify that, or can I? Is there anything I can do? So what we're going to end our section with is just a quick, brief introduction to powers of I and how to resolve them. So we already know that I is just I. That's my definition. It's the square root of negative 1. Then we already saw that I squared. What's I squared equal to? Remind me? Negative 1. So we know those two powers. So what I'm going to do now is I'm going to do a little busy work. And we're just going to go through and we're going to see what happens next. So the next one I would say is, okay, we've got I to the first power. We've got I to the second power. So then the next one is, what's I to the third power going to be? Well, I'm going to write I to the third power in terms of things I already know what they are. And just as a quick review, when I multiply two things, what do you do with the powers when you multiply the bases? You add the powers. So x to the second times x to the fourth would be x to the sixth. 2 plus 4 is 6. Okay, so here we go. I know what I to the first is. I know what I to the second is. So I'm going to write I to the third as I to the second times I to the first. 2 plus 1. What's 2 plus 1? It is 3. Everybody says with enthusiasm. Yes, 3. Now let's simplify, and we're going to see what I to the third becomes. Well, we've said this 100 times. Here's 101. I to the second is negative 1, so this becomes negative I. So I to the third reduces to negative I. The next one, I to the fourth. Well, again, I'm going to write I to the fourth in terms of things I already know the answer to. And so I to the fourth is going to be 2 plus 2. 2 plus 2 gives me 4. I squared is negative 1. You already told me that a dozen times. I squared is negative 1. So negative 1 times negative 1 becomes, so I to the fourth becomes 1. Now this is good for me because that means every 4 i's becomes 1. So if I can break up any bigger power now into groups of 4, every I to the fourth becomes 1. So for instance, my example is I to the 21st. Now I'm going to do this the long way, and then I'm going to show you the short and sweet and easy way. But we know that every I to the fourth is 1. So I'm going to take these 21 i's, and I'm going to break them up into 4 packs. Okay, so here we go. I to the 21st is I to the 4th times I to the 4th. How many i's is that? You keep track. I'm not that smart. That's 8 times I to the 4th. How many is that? I to the 4th. How many is that? 16 times I to the 4th. That is 20. So then I have one more. And again, why did I pick all of these I to the 4ths? Why, instead of doing I to the 3rd, I to the 2nd, why did I pick I to the 4th to break it up into? Because I to the 4th is, all of these now are just 1 times 1 times 1 times 1 times 1 times I. And so I to the 21st is equal to I. They're the same thing. So, of course, you see that one of your examples is to do I to the 82nd, and clearly I do not intend for you to do I to the 4th over and over and over again. What operation am I employing when I take 21 and I break it up into how many groups of 4? What operation is that? It's division. Here's how to do this nice and quick and easier. I'm going to take the 21 and I'm going to divide it in groups of 4. Okay? The groups of 4 represent my I to the 4ths. How many times is 4 going to 21? This 5 represents the 1, 2, 3, 4, 5 I to the 4ths. I don't care about that at all because all of those I to the 4ths are 1. What I care about is the remainder. 21 minus 20 is 1. And that's why I to the 21st, here's the shortcut, I to the 21st is equal to I to the 1st. And so what happens if you just went through and did this over and over and over again? What you see is that I is equal to I to the 5th because there's one group of 4th, and I squared is I to the 6th, I to the 7th, I to the 8th because that's 4 plus 4, and then it just keeps repeating. If you're interested in math, this is called a modular arithmetic system. Okay, it's fantastic stuff. It's really good if you want to go and if you're ever interested in doing anything mathematical, but maybe you're like, I do not want any more math in my life than I already got. Okay, so what I would like you to do is just employ this tactic of dividing, and I would like you to simplify what is I to the 37th equivalent to. So I'm going to take my 37, I'm going to break it up into groups of 4 because that's my I to the 4ths. And so 4 goes into 37 and 9. 9 times 4 is 36. I didn't do good addition when I was making the sheet, so my apologies. 9 times 4 is 36, leaves me a remainder 1. So I to the 37th, it's equivalent to what we just did, I to the 21st. They are both equal to I to the 1st power. Do the last example or last exercise, I to the 82nd power. What does that become? So once again, I'm going to break this up into groups of 4 because every 4 i's makes 1. So I'm going to take my 82, break it up into groups of 4. So 4 goes into 8 twice. Bring down the 2. 4 goes into 2. It doesn't. Okay, so that's great. These 20 I to the 4ths, I don't care about. What I care about is the remainder, which is 2. So I to the 82nd is the same thing as I to the 2nd. And I to the second we know because it's one of our 4 basic values. I to the second is -1. All of your answers should turn out to either be I to the first, I to the second, I to the third, or I to the fourth. And then you simplify it. I to the second is -1, I to the third is I to the fourth is +1, and that is how you simplify powers of I. Yeah.
So the remainder that you have is going to be the exponent of I.
Exactly. Well stated. Nice summary.